what we did for the last two videos was the regularization and the renormalization of the lambda phi 4 theory, right? We used the scheme that used the Pauli-Wheelers for the regularization, and the renormalization was done enforcing a physical mass for the states of the theory, right? And then we calculated the counter terms, which basically does the whole renormalization of lambda phi 4. We didn't prove that yet. In particular, we'll see if there are other maybe diverging loops in lambda phi 4 in the next video. But now what I want to introduce is an alternative method for regularization. The thing is, Pauli-Wheeler's method can be quite complicated in most practical cases, right? For practical reasons, because you're increasing the powers in the denominator, that means you get higher order polynomials in the denominator, which can be complicated to deal with, right? That's a practical aspect. But also, there are some cases where Pauli-Wheeler's fails to keep all the symmetries in the theory, like we'll see eventually in non-abelian gauge theories. So we want to have more tools in our tool set to deal with these theories. Also, by looking at an alternative method for regularization, we'll be able to compare Pauli-Wheeler's and the new one, which I'm about to introduce, and see, I mean, when you do regularization, you get the impression that there are a lot of arbitrary things going, a lot of constants that are non-physical, and by comparing these two methods, we'll be able to see how these things are eliminated from observables, which is always nice and gives us a sensation of safety, right? So the regularization method I want to introduce today is called the dimensional regularization. And these are some references where you can find it, right? And the idea is also based on something that we looked at when we were discussing Pauli-Wheeler's regularization, right? We are looking at integrals that quite generally look like that, right? You have some powers. Once you go to the Euclidean and write everything in terms of this module of the momentum, right? You quite generally have some power of the momentum in the numerator and another power in the denominator, and we you can see here that on the upper limit of the integral, so the ultraviolet of the theory for very high momentum, right? You have the situation where if this is the power in the denominator is not big enough as compared to the one in the numerator, you get, in this case, if it's equal to n plus 1, we'll get a log divergence, and if it's even smaller, m is even smaller than this limit, then you get higher and higher powers, right? You can get square divergence, quartic divergence, so on and so forth, right? And Pauli-Wheeler's basically helped us increase the power of momentum in the denominator. Right? The whole idea of the dimensional regularization is to lower the power in the numerator. So you go the other way. You leave the denominator as it is, and you try to lower this power up here. Right? But in most of the loops we were looking at, this power of momentum in the numerator came from the integration measure, right? Once you go to spherical coordinates, you get some power here that depends only on the dimension of the space-time, right? In our case, it was momentum to the cube, right? And of course, in some particular theories, you have more powers of momentum in the numerator. You can think fermions, for instance, they have some powers there. But if you want a method that you can apply to any theory, right, there's no way to lower the power in the numerator unless you mess with the dimensions of space-time, right? And of course, you can think of physical situations where this happens physically, right? You can think solid-state problems, like condensed matter problems, where the whole dynamic is contained to a surface in momentum space, or and then naturally your system is lower dimensional, right? That is not 4 dimensions in space-time, can be 2, can be 1, right, plus time. And in those physical cases, of course, you can build field theories which are finite, right? You can do renormalization of finite theories, right? Which is nice and well, but it does not help us in the problem we have at hand, right? Which is 4-dimensional Minkowski space, and we want to be able to regularize theories there. So what we're trying to do here is something more complicated, right? We want to think in these loops. I don't know, I'm calculating some loop, right? And it is somewhere you have integrals over the loop momenta, right? So you have a lot of constants here, functions there, right? But somewhere you have these, right? And you want to think of this guy as a function of this parameter d, right? Which is the number of space-time dimensions in your theory. And now we want to make an analytic extension for dimensions which are not even integers, right? You want to consider even the case where you have d being any real or complex number, right? And that's the whole thing we'll be trying to do today. Dimensional regularization is very advantageous from the point of view of algebra, right? You're not increasing these powers of the polynomials in the denominator, right? So calculations actually turn out to be easier, right, and shorter in this method. Also, as I said, you keep more symmetries. Although there are some that you still break with dimensional regularization, you have to be careful about those. We'll explore that more in the future when we get to that problem. The main disadvantage of dimensional regularization is that the physical interpretation is not that clear. You can convince yourself that you're really changing the UV because that's where the divergence was, and it won't be there anymore, right, in the limit we're taking. But it's not clear why or how you're doing that, right? Other than this very simple power of momentum argument I just gave. Right? And this interpretation is difficult to the point that there's this very funny quotation here by Sidney Coleman, right? This is in the book where they made a transcription of his lectures, right? And I hope I'll convince you that it's not that bad, but you have to keep your mind open because mostly we're doing analytical extension of a function, and it's kind of the interpretation of this is always hard unless you're going back to the limit where d is an integer again. And that's what we're doing, right? We take d to be slightly smaller than 4, and we always be looking at the limit when d is coming back to 4 dimensions from the lower side. Of course, in this case I have to lower dimensions to make my integrals converge, right? So let's start with a particular example, right? And we're trying to do lambda phi 4, right? We have the 4-point function and the 2-point functions we calculated over the last 2 videos. And we're going back to those, starting with this 4-point function, which we have written before. I'll just rewrite it again here. This is just the Feynman rules for it. So there are two vertices, right? Symmetry factor, an integral over the loop momentum over 2 pi to the 4, and then these 2 propagators here, which are I over k square minus m square plus I epsilon, and the other propagator, which is I over, now this one, right, k plus p square minus m square plus I epsilon. Right, so we want to look at this guy. Now using this idea of the dimensional regularization. So now we're taking a limit, right? Eventually I forget this limit, but it's always implicit in the idea of regularization that you have some parameter there that once you take to a particular limit, you recover the divergence. And in this case, it's over the dimensions of space-time, which are smaller than 4, and going back to 4 from this lower side, right? And that changes this integral in the following way, right? Which is, this becomes d, this one becomes d, and these four momentum scalar products are done over more components of the momentum now, right? I'm assuming this has some interpretation even when I'm making this guy non-integer. That's the extension I'm doing, right? And now if I change this, right, without changing anything else, clearly I changed the dimension of the integral, right, in terms of dimensions of energy, right? And to compensate for that, I'll introduce another parameter. Let me put it right here. So I'll color this one blue. Same here, right? And now I have another parameter that I'll call mu. This is a parameter that has dimensions of energy too, or mass, right? Which is the same since I'm in natural units, right? And this will be to the power 4 minus d, so that it compensates for the change in the integral itself, right? So in here, I introduced two parameters, important to keep that in mind, right? One is the regulator, which is d, right? D here is the regulator. And another one is mu, which is an arbitrary mass scale, right? To see the job of this mu more explicitly, let's take a look at the dimensions. So in 4 dimensions, right, this has d4k has dimensions of mass or energy to the 4th. So dimension 4 in natural units, right? Now I change that to dk, right? It has dimension d. At the same time, mu has dimension of, as I said, of mass or energy, right? So dimension 1 in natural units. And that means that the product here keeps, of course, dimension 4, because if you add up those two, you still have 4, right? So I'm keeping the dimension of this term unchanged. And in case you're wondering, what I mean by this bracket notation is just the dimension of the quantity calculated in natural units, right? I forgot to say that before, but that's all there is, right? Now, the introduction of this arbitrary scale here is optional, right? It's conventional. Some of the references I just gave actually don't do it. Don't introduce this at all, right? And then the consequence is that you have a dimensionful coupling constant, right? That's easy to see if you do some dimensional analysis in the Lagrangian itself, right? We know that the action needs to be adimensional, right? Which is an integral of the Lagrangian. So the dimensions of these need to be 0, right? And this integral in dx, right, has dimension minus d, because space and time have dimension of -1 in natural units, right? Which means that the Lagrangian in arbitrary dimensions needs to have dimension d, right, in order to compensate for these and get you an action which is adimensional, right? And then you look at the Lagrangian for lambda phi 4 using this. I'm not putting all constant, but del mu phi, del mu phi minus m square phi square. There's a 2 here, but I don't care too much. Minus lambda 4 over 4 factorial, right? From here, now that you know the dimension of the Lagrangian, you can get the dimension of the field, right? Either here or here. So, for instance, on this side, the dimension of the derivative is 1. So these two derivatives contribute to a total dimension 2, right? Same here with this mass, right? The dimension of mass square is also 2. And that means that this phi to the square here, the dimension of phi square, needs to be d minus 2. So the total is 2, either on this term on the Lagrangian or this one. And that means that in arbitrary dimensions, the dimension of the scalar field is d minus 2 over 2, which is an important thing that will play an important, very important role further on, right? We'll be doing a lot of dimensional analysis on quantities when we are trying to do a more general approach to renormalization. But for now, what we can see from this is that if you go back to that dimension, now to this lambda 5 to the fourth term here, right? You see that this term, again, every term in the Lagrangian needs to have dimension d, right? And that means that the dimension of lambda plus 4 times the dimension of phi, which is this, right? D minus 2 over 2 needs to be equal d, right? And then you can solve this and see that the dimension of lambda will be 4 minus d, if you think in terms of the Lagrangian, right? So not doing anything to compensate for the change in dimensions will end up with a dimension-full coupling constant, right? But that's okay. You can keep it like that, and that would mean that the expansion for the 4-point function will look something like that, right? Minus I lambda plus, and here comes the first loop, will be something like minus I lambda square. And again, many things, but the important part for dimensional analysis here is the integral, the measure of integration, and the power, the total power in the propagators, which is something like 1 over k to the fourth, right? I just have to look here, and you see that this part has dimensions of 1 over momentum to the fourth. And you see that here everything is working well, right? So lambda now has dimensions of 4 minus d, right? And this term, right, has a total dimension that comes from this guy, and this one, which is lambda square d dk over k to the fourth, right? The total dimension here, just have to use the dimensions I calculated above. So the lambda is to the square here, so it's 2 times 4 minus d plus d minus 4, right? D from here minus 4 from here, which is 4 minus d. So the sum, and of course there are other terms, I'm just stopping here, right? The sum makes sense, the dimensions work fine, right? But you need this dimension-full lambda, right? Introducing this lambda here in the integral makes it so I can keep lambda adimensional. So it's equivalent, if you think again in terms of the Lagrangian, of making a change in this lambda phi 4 term up here, which is exchanging lambda by mu 4 minus d lambda. So this guy now shows up in every Feynman rule, right? And carries this 4 minus d dimension that is being carried by lambda if I don't do this, right? The main price of not doing this and keeping this lambda dimensional is that eventually logarithms will show up, and you have logarithms of dimension-full quantities, which is a bit odd. But again, you can fix that at the very end of the calculation. When you go back to the four dimensions, you look at these logarithms and you see, well, this is a dimension-full quantity. I can introduce a division, but some other arbitrary quantity here that has the same dimension to make the argument of the logarithm adimensional. That's how Peskin does it, right? So you can take all these approaches. We'll be doing it from the start with this quantity here. The important thing is to not confuse this quantity with some UV scale, right? The capital lambda we had before, right? This is not some high energy scale, it's some arbitrary scale that I can keep it without any interpretation if I want. Results should not depend on this, right? But I can even use it for something, right? I can decide to use like this arbitrary scale as part of my renormalization conditions if I want to. We actually do this eventually. But be careful to not confuse this scale with something that you should take to the UV at some point, right? To infinity, because that's not it, right? The regulator here is really the number of dimensions, d, which will be taken to 4 at the end, right? So don't be confused by mu. Now we can actually go ahead and do the calculation, right? So we use this expression here, right? And once you have basically put your regulator in here, right? Now the rest is very similar to what we did in the Pauli-Villar's case, right? It's all the same tricks, right? So we start with Feynman parametrization, right? We want to make these two polynomials here into one, right? I'll do some redefinition here because these epsilons, I'll call something else epsilon. So I'll call these two guys epsilon prime, right? Because I want to call this guy up here 4 minus d. I want to call this epsilon because, of course, once d goes to 4, right, epsilon goes to 0, and use these as a expansion parameter, right? So Feynman parametrization for these two guys is pretty straightforward. So I'll just repeat the part that needs to be repeated. Mu, I'll actually write in this way, mu to epsilon. Remember, this epsilon is now not the one in Feynman prescription, which I'm calling epsilon prime, right? And Feynman parametrization is simple. In this case, it's just two polynomials, two terms, right? It's a simpler case before because I'm not doing Pauli-Villar, so I'm not introducing another term in here, right? And this is just 1 over a big thing, which is x k plus p square. Let me write again. K plus p square minus m square plus I epsilon prime. And here goes a 1 minus x k square minus m square plus I epsilon prime. And this is all the power 2. Right? Let me do this again. So that does the Feynman parametrization, right? Again, I use the same tricks I used before. The first thing I want to do is to take this denominator, which I'll call d, right? And actually, there's two i's missing here. So there's a minus up front, right? I square here. And I want to take this denominator and first expand it and then complete squares here, right? So that denominator is what we did in the previous video, so you can go back and look, but it's very simple, right? This is, if you do all the algebra, it's just k squared plus 2k scalar p x plus p squared x minus m squared plus I epsilon prime. This is just expanding this, right? But then I can define some L square, which eliminates this cross term between k and p, right? And then I complete the square. and define this delta, this big delta, plus I epsilon prime, where the big delta square is m squared minus x, 1 minus x, p squared. We did exactly this calculation before, so I'm going a little bit faster here, right? And L is defined, L mu is just k mu plus x p mu, which is a change of variables I can do now in this integral, right, to eliminate this cross term and get a simpler integral. So what I'm getting now is this. So this part I'll just copy. This becomes the integral in d dl over 2 pi to the power d, right? There's an integral in x, 0 to 1 dx, and this whole thing has become just 1 over L squared minus delta squared plus I epsilon prime squared. Right? And then once you get that, the next trick, of course, I want to write these in spherical coordinates, right? And to do that, first I need to go to a Euclidean space, right? So let me just copy this diagram so we don't forget what we are calculating down here. So now to go to Euclidean, right? I do the same thing I did before, a Vic rotation in dl0, right? And that produces an I up front here. So let me put that in a different color. Just I came out here. The rest is the same. The integral in x I'll bring to the front. Oops. I want to copy it. So this guy became L Euclidean, and that's the I that came to the front there, right? And then the denominator here, right? This guy becomes minus L Euclidean, right? But then there's an overall minus sign here that I can take outside, so this becomes a minus. But in this case, it's to the power 2, so there's no minus going anywhere, right? I can do that for free, and I get this expression, right? So now I want to write this guy in spherical coordinates. Of course, that was pretty easy in 4-dimensional Euclidean space, but now I want to generalize these to arbitrary real dimensions, right? Not integer dimensions. So I can write, right? I'm defining a lot of things now, which make this analytical extension, right? So I can write this. Now this is the module of this momentum, right? This is the momentum, and here I'm using something that goes back to what should when you go to integer dimensions, integer positive dimensions, right? And I'm writing this guy, which is a generalization of the solid angle, right? And there's a trick to actually figuring out who this guy is, right? All we have to do is remember Gaussian integrals, which are the favorite integrals for physicists everywhere, right? So take this integral here. That you know, right? And now let's raise it to the power n. Right, so I'm taking this integral and now raising it to the power of n. on both sides of that equation. Right? Now, this integral is the same, right, of course, as a multidimensional integral in n dimensions. So this is the same as writing. I just have to rename variables here, and this will be the same as a dnx of the exponential of the sum over of xi squared over n, right? You have n terms like that. Right? And that I can write, if n is an integer, right? I can write these as the integral over the solid angle, n, right? Integral from 0 to infinity of the module of this n-dimensional vector I just created, right? Times the exponential of minus x squared, right? Again, the module of this guy, which was appearing here anyway. Right? Now I can rewrite these as integral over dx squared. Right? I can just write using, right, that dx is equal to dx squared over 2x, right? Substitute these here and get, let me write this down here. I have d omega n and an integral from 0 to infinity of dx squared. This changes the power of this guy. Let me put this factor of half out here, right? And now I have x n minus 2 because of these x here, right? And exponential of minus x squared. And now this guy I want to write as x squared to the power n minus 2 over 2, right? And now I wrote this integral here, for which I know the answer, right? This is just pi to the n over 2. If you look here and here, now I have both expressions, with the exception of the solid angle, I have both expressions written fully in terms of this n. And now I'll do the extension, right? I'll do the extension to taking n from an integer, a positive integer, to anything, essentially, to any complex number. And the reason I can do that is because this is already written as a definition of a gamma function, right? For any integer, but we know that the gamma function is has an analytic extension to the complex domain, right? So what I'm using here is the definition of a gamma, the integral definition of the gamma function, which is this one. It's exactly I have here, right? With t being x squared and z being n over 2, right? We have n over 2 minus 1 right there. So now what we have is pi, I'm generalizing to d, right? Pi to the power of d over 2 is equal to what I have here, so d omega d times gamma, and again z is n over 2, that becomes d over 2, right? Which now I can use to isolate the integral in d omega, right? And write the expression we want, the generalization we want, right? Which is that d omega in d dimensions will be 2 times pi d over 2 over gamma of d over 2, right? This is an important extension, and we'll use it a lot when we're doing dimensional regularization, because the integrals in angles can always be done like that, right? Because we take care of writing expressions which depend only on the module of the momentum. So we'll be doing just the integral in omega using that expression. So now I can copy this down here. Let me take it all the way down here and write this integral in spherical coordinates, this generalized spherical coordinates, right? So let me just copy this whole part here, right? This is fine. Now this part I'll write in terms of the integral in the module of momenta. So now I have a dl Euclidean over this times this denominator. This does not change. I get also from this part an LE to the power d minus 1, right? This is all just repeated. And of course, now I get the new piece, right? And since nothing here depends on these angles, right? This is just the omega d, right? Which I can use this expression to calculate. So let's do that, right? And write down here again. This part just repeats, right? Eventually I have to write this integral in dx, but does not depend on any of the integration variables. So let's put this right here from the integral in the solid angle. This is 2 pi d over 2 over gamma d over 2, right? And then there's this integral in x. First, the integral in x. Let me copy the whole thing right here. Now, let's just improve this a little bit, right? And again, this integral can also be manipulated, right? Again, I can exchange this guy, right? Let's also bring this guy outside, out of the way. Let's put it right here. Right? Does not look very pretty, but it's fine, right? And I can exchange this guy, right? Again, I can make this a dl square over 2, right? And then this lowers the power of this guy by 1, right? Because dl2 is 2, is dl, there's a power of le in the denominator here that compensated there, right? And this I can rewrite in this way. This is just le square to the power d minus 2 over 2, right? And this is another integral that we have done before, right? This is the definition of a beta function, which then can be written in terms of products of gamma functions, right? So go back to the previous video, you find we were calculating this, right? And this is just 1/2 of 1 over delta square minus I epsilon prime 2 minus d over 2. Right? Of course, before, when we did this calculation before, there was no d, but this is just a change in the constants in the definition of the parameters in the definition of the beta function. And the gammas that show up here is gamma of d over 2 gamma of 2 minus d over 2 over gamma of 2, right? So this integral is now done, right? I'm left with the integral in x only. There's a lot of simplifications we can work out here. So for instance, let me choose appropriate color. So this guy cancels this guy, right? This factor 2 here, say this factor 2 here can cancel this one. And now let me put everything together and see if there's more simplifications we want to do. So I'll also reorganize stuff a little bit. I'm keeping this I here because I want to keep track what is coming from the integration and what is coming from Feynman rules, right? So this minus I is coming from the integration process. This is just the Feynman rule, right? I'm bringing the mu to the right here because I want to put everything that depends on this arbitrary dimension together. So now I have a d over 2. I still have this 2 pi to the power d down here, right? Now there's this gamma that I can put out to the front, but I remember I define epsilon as 4 minus d up there, right? In a long time ago. Let me see if I can find it. Here, epsilon is 4 minus d. I can use that definition of epsilon here too. So this gamma of 2 minus d over 2 is just epsilon over 2, right? And then the integral in x. 0 to 1, 1. This is the only thing that depends on x, right? This is this delta square right here. This is delta square minus I epsilon prime, for the dx here. To the power, again, 2 minus d over 2, I can just write as epsilon over 2. This is not a very clear epsilon. That's not better. Now it is. Okay, so that's the expression, right? And it's important to notice that the divergence, right? Our divergence is still here, right? In fact, it's now encoded in the poles of the gamma function. So this is nice plot on Wikipedia, reminds us of how the gamma function behaves, right? It's a function that is analytic everywhere in the complex plane, with the exception of real numbers from 0 down, negative integers and 0, right? So 0, minus 1, minus 2, all have simple poles, called simple poles in the gamma function. So what I'm saying is that this function has poles, that's right, like that, poles, in z equal to 0, minus 1, minus 2, minus 3, and so on and so forth, right? Since here I have the gamma not of epsilon, but epsilon over 2, that means if I think of these in terms of epsilon, the poles will be in epsilon equals 0, minus 2, minus 4, minus 6, etc., right? And then I can think in terms of d, right, which is 4 minus epsilon, right? That means I'll have poles for this function in 4, 6, 8, or more dimensions, which makes sense, right? We know that this integral, remember we're talking about the 4-point function for lambda phi 4, and we know this guy has a logarithmic divergence. So at 4 dimensions, with 4 here, it has the very, I would call the least divergent divergence possible, which is the logarithm, right? That means that if you decrease the dimension a little bit, it becomes a finite integral. So there are no divergences for dimension lower than 4. But of course, if you increase the dimension, and here you can see the the integer dimensions where there will be problems, then you're increasing the powers in the numerator, and you find divergent theories above dimension 4, right? So you see that our divergence is now becoming this pole for 4 dimensions, right? Is now becoming this pole at z equals 0. So now what we need to do to make this even more explicit, right, is expand everything that depends on epsilon here, this part, these two, this one, and this one, in close to epsilon equals 0 to see how the function behaves near this pole here, where we recover our physical case, right, when we go back to 4 dimensions. This is really just a matter of doing the expansion for epsilon close to 0 in every bit here, and then multiplying them all together is a bunch of algebra, right? But since we are in the 21st century, I decided to use this as a little bit of an exercise on a 21st century tool, right? So this is what we want to expand, right? And this is Wolfram Mathematica, right? And we will use it to do this. So let's go and do this term by term. So I'll call this first term 1, right? Is let's call this start with the gamma, right? So Mathematica has a gamma function, right? I'll call epsilon epsilon. So what I want is to do the Taylor expansion for gamma of epsilon over 2. This looks nicer like this, right? And in order to do this, I just have to call a series, right, of the preceding function, right, for epsilon near 0, and I'll take this to 0 order in epsilon, right, because the terms that are linear or bigger powers in epsilon will all go to 0 as epsilon goes to 0, right? And this is the symbol that applies this to the preceding thing. And then I can see the expansion, right? So it's just a 2 over epsilon minus the Euler-Mascheroni constant, right? This is 0.577 something, just a number, right? In terms of order epsilon to the 1. So this is this small part here. Let's do the same for the other parts. So term 2, let's take the one inside the integral. So that's just 1 over. I'll just call delta 2 like that, because I don't need to put it to square. That's the complex I. And I'll call epsilon prime, epsilon p, like that. And this is to the power of epsilon over 2. This is useful to see if I wrote everything correctly. So that's exactly that term over there, right? And now I can apply this series, same series here again. Now I'll go to the power of epsilon, right? Because these terms will be all multiplied. But now gamma produce a 1 over epsilon here. So I need to look for linear terms in epsilon in the other terms, because they can multiply this first one and produce something finite, right? So now I run this, and this is the expansion of the second term. So 1 minus half the log of all of these. This is the natural logarithm, right? In terms of order epsilon square. This is fine, right? Let's do another term. So let's call this term 3 is, let's say, this mu here, right? I'll write mu as mu 2, which is mu square, to the power epsilon over 2, right? I did nothing. This is just mu to the epsilon, but I'm interested more in this mu square because you'll see later, it has the right dimensions for what I want, right? And then I just have to apply the series. Again, I'll go to linear order in epsilon, right? And here is the expansion down there, right? Now let's write down here term 4. I'll just use this whole thing here, and that's it, right? Term 1 was here, term 2 was this, term 3, and now 4 will be everything there. Let me see if I can write everything in the same screen. This will be pi to the power d over 2 divided by 2 pi to the power d, right? That's what I have up there. Let me check, just see if I made any mistake. So yeah, that looks good. Also, I want to do the expansion in epsilon, so I will exchange d for 4 minus epsilon, right? That writes the expression in terms of epsilon, right? And then I do the series expansion using this command right here. And there it is, right? There's a bunch of constants, right? Now I can multiply these 4 things, right? Term 1 times term 2, term 3, and term 4. Be kind of okay, but I can improve the visibility here. And now you can see there's a term 1 over epsilon, right? A bunch of constants. This all is independent of epsilon. And then order epsilon to the 1 terms. You see, Mathematica does well with this order epsilon terms. It does the multiplication and bunches everything that doesn't matter anymore over here, right? I can even expand for this other epsilon, this epsilon p that is here, is epsilon prime, right? So I can take this and do now a series. This indicates I'll take the result from the previous line, right? And do a series in epsilon prime close to 0. Also, I'm only interested in terms linear in epsilon, right? That does this thing, right? It's here. Now I also expanded the epsilon prime. This is just a log of delta 2 plus something. And also I can call this epsilon prime divided by this epsilon prime prime, right? It's just another epsilon, right? And I can do this normal to eliminate these order epsilon prime square or order epsilon symbols there. And then I have this expression, which now I'll put back on my blackboard. And there it is, right? I copied the result from Mathematica here and I have it written up here, right? So you see it's a 1 over 16 pi squared common to all terms here, with the exception of this one, but I compensated that by a 2 over epsilon over here, minus the constant, plus I epsilon prime prime here, because I incorporated these delta on the prime, right? That's the log of delta square, log of mu square, and here you see why I want this mu square, because now I can group these two together. This is the log of something dimensionful, right? Delta has dimensions of energy square, right? So what really makes sense here is minus the log of delta square over mu square. And this is also where you could see, if I didn't include this mu square from the start of the calculation, I would have this log alone, making it obvious that somewhere there's a constant, dimensionful constant hiding inside the divergence, right? And you can subtract it out to make this log make sense. And then a bunch of numbers, right? This is a number, this is another number, right? Also, I can take here epsilon to 0, because now this epsilon is summed with a lot of constants, right? So it's a small number, goes away. I don't need to keep track of that epsilon prime anymore, right? And then I can use this expansion up here, right? These are all these terms that are here, and I can rewrite the 4-point function. Let me erase this thing I brought from Mathematica and put our expression here. So there's a minus I, this I can copy, keeping it here. 1 over 16 pi square, right? The integral in x, And now this thing, right, which is a 2 over epsilon minus this log ln delta square over mu square, right, plus a bunch of numbers. I'll just call these big N, right? They don't matter too much, and I can always write these numbers as the log of something, throw that something down here and redefine mu. So you see, these numbers can always be absorbed somehow, and there's a lot of different ways you can deal with these numbers that are here, and that leads to different schemes of renormalization. We'll discuss these a little better further on, right? Now just let me just explicit delta, because now we want to use this expression for some. So delta is m squared minus x1 minus x p squared over mu squared here. So I just wrote lambda explicitly, right? And we know what we are calculating here. Really, we have called before the 4-point function, right? This is gamma L of p squared, right? The dependence on p squared is right there. And now, if you remember correctly, right, we have separated these integral, these loop contributions in two parts, right? We use the Taylor series to separate the gamma L of 0, which was the divergence, from something that is the first derivative of gamma L, which is gamma tilde, which is finite, right? So let's use the same idea here, the same technology here, right? Starting with the divergent piece, right? So the divergent piece is just gamma L of 0. Right? I just have to repeat everything here, and now I'll just simplify everything. There's a -1 coming from here, so that's just I lambda square, right? There's a 2 here, so it's 32 pi square, right? Integral from 0 to 1 dx of this thing, right? But now with p going to 0, so this whole piece goes away, and I'm left only with the log of m squared over mu squared, right? Plus numbers, I don't care too much about, right? And this, of course, is integrable in x in a pretty trivial way, because there's nothing depending on x anymore. And also it's just from 0 to 1, so this is the result of the integral, right? So we actually got the divergent part for the 4-point function in dimensional regularization, right? And other than the difficult conceptual ideas behind the dimensional regularization, you see that the actual algebra was simpler than in the polyvillars case, right? Which we want to compare this with now, right? So let me write here the polyvillars result. So I'll call this gamma L of 0. Put a PV here to remember this is coming from polyvillars, right? And this was a very similar expression actually. So see the coefficient here is exactly the same, right? And also you have something that depends on some logarithm of lambda squared over m squared, right? So you see, it's not the same, right? Of course, these two things do not need to be the same because they're not physical. They don't show up in any physical measurement. So they have no obligation to agree in different regularization schemes because they will cancel each other, right? But there's a mapping you could make here. Suppose you do a calculation polyvillars and you want to know what's the equivalent result in dimensional regularization. And by looking at these expressions, right, you would say that the mapping is just exchanging this thing, right, 2 over epsilon. log of mu square, right? I can change the sign, bring the mu square up here, and then the log of the mass cancels from both sides, right? Plus the numbers you exchange by the log of lambda square, right? Which is a log divergence, right? This is a 2 that comes out here. So I would say this is the mapping between these two regularization methods, right? Of course, this is, we don't know at this point if this generalizes to other loops, but at least in this case, that's the mapping you could find. But now we can extract a finite piece from this 4-point function, a finite piece that actually shows in experiments. Remember, that finite piece decides if you measure the coupling constant at one point, right, the S matrix element at one point, the finite piece of this 4-point function will predict what's the measurement in other points. So that's a prediction, and it's something that you can verify. Let's see what happens with that function. So that function is defined, is what we call gamma tilde, right? So I gamma tilde, I gamma tilde of p square, right, is equal to I gamma of p square minus I gamma 0, right, which now we can calculate pretty easily, right? Let me just copy this guy down here. I have to do the simplifications here again. So this is just I lambda over 32 pi square, right? So this is just I gamma of p square. And of course, the I gamma 0 is the same thing without this part, right? Because p square is just 0. There's a minus sign between these two pieces, so you see a lot goes away, right? The 2 over epsilon goes away, right? The log of mu square, right? I can write these as plus the log of mu square goes away, right? These numbers go away, right? In fact, you can see just by these 3 cuts, these 3 cancellations here, everything that depends on these spurious parameters from my regularization go away, right? The number, mu, epsilon, right? Epsilon is actually what's concealing between these two pieces is the divergence, right? And you get something very, very nice here. This is actually a very cool result, right? This is, I'll bring a minus out here and compensate this by these 2 logs, right? 32 pi square integral from 0 to 1 dx log of, I'll put this one first, m square minus x 1 minus x p square, and that's the minus that went outside, and this one, the minus go outside, becomes a plus, and then it goes into the denominator, right? So that's the integral I have to do. There is actually, I can do this integral by parts, right? I can just rewrite these as the sign changes, right? And write these as an integral from 0 to 1 of x minus 1. This is the guy that becomes dx here, right, in an integral by parts. And then I have the primitive of this one is just 2x minus 1 p square over m square minus x. 1 over x p square dx. And actually the terms at the edges here are just zeros, so there's only this piece, right? Which is exactly, now that I did an integration by parts here, so you can try that and check. But the point is that this integral is exactly the result we got from Pauli Wheeler's, right? So not only all the constants that depended directly on dimensional regularization went away, right? But also you got the same result, which is, I mean, it's a kind of a sanity check, right? Means these two regularizations are agreeing on the physical quantities of your theory, right? It's well, it had to be this way, but it's still amazing to see it works after all these calculations, right? And so now, if you want to do all these conclusions that we got on the end of the previous video to using Pauli Wheeler's, you can do the same now with dimensional regularization, because this part is exactly the same, right? Now we can apply the same to the 2-point function. I won't do that in detail here. I'll leave it as an exercise. Right? Most of it is just the same idea, and I'll show the result and comment on the result. So this is the 2-point function for the lambda phi 4 theory, right? As we know, we have analyzed this. This has a quadratic divergence and a logarithm divergence in here, right? And once you do dimensional regularization and follow the same steps we did for the 4-point function, you get this expression right here, right? Then, of course, you can do the expansion for all these guys near d equal 4, and that's what you get for the pole in d equal 4. There are a few important things here which are a little bit different from the 4-point function, which is this guy now has poles in two places actually, right? Not just d equal 4, but also d equal 2. Of course, both of them have poles for d bigger than 4. But this guy, even if you go to small dimension and you go all the way to dimension 2, there's also a pole there, because if I put a 2 here, this will be the gamma of 0, right? So there's two different poles here for dimensions 4 or less, right? This is actually the only kind of hint that you get in dimensional regularization on the fact that this divergence was quadratic to start with, right? Because if you look here, you go near d equal 4 and you look at this expression, you see that the divergence here is exactly, looks the same as it did in the case you only had a logarithmic divergence. It's just a 1 over epsilon, right? Which is expected, right? It's just a reflection that if you look at the analytic structure of gamma functions, the poles are just simple poles for every z 0 or minus 1, minus 2, minus 3, so on, right? They are all simple poles. So no matter where you are, if you go near one of these poles, it will be something like 1 over epsilon, right? So there's no surprise here, right? But suppose we want to compare these now with the Pauli Wheeler's result, which I repeat here, right? And you want to find like that matching, like that dictionary between the dimensional regularization and the Pauli Wheeler's methods, right? You have to decide what divergence you match here. Let's suppose you want to match the square divergence, which is the most serious one on the Pauli Wheeler's case, right? You try to find a dictionary between these two parts, right? There's some cancellations here of constants, but that's equivalent of matching these minus lambda square, right, to m square times everything that's in here, right? Which is a very different matching than what we got from the 4-point function, right? This is completely different, right? It involves even the physical mass in the matching, right? Now, on the other side, if you want to match the logarithmic divergence, on the polyvelar side, right, with what you're getting from dimensional regularization, now there's a lot of simplifications here. You see the mass is on both sides here, simplifies, logarithm of the mass too, right? You end up with this map between the two methods. Which now, let me finish writing it, right, is exactly the same map you got on the 4-point function case, right? This is an indication. Of course, this is just can be seen just as a coincidence because I didn't do any proof here to any generality, right? But that's an indication that the dimensional regularization is really only seeing the logarithmic divergence that you see on the polyvelar side, and is regularizing polynomial divergences like lambda square, lambda fourth, lambda anything to 0, right? Actually, you can find a more serious version of this argument in this reference, which I indicate for people that want to really look into the mathematics of this, right? I want to go that deep on the dimensional regularization, but there is this idea that the dimensional regularization is really only sensitive to the coefficients of these logarithmic divergences in cutoff based regularizations, right? You see this number up here is the same, right? The coefficient of the log of lambda, right? You can even remove a 2 here, which will be the same as these two. So the log of lambda has the same coefficient that this 1 over epsilon here. And this will become very important further down the line because we'll be using dimensional regularization quite frequently, almost exclusively, right? And now, of course, you can go forward, right? And do the same we did at the end of the last video and calculate the counter terms in this version, right? In this regularization. I'll just write them here. Again, it's just a little bit of algebra now using these expressions, right? And you can get the counter term for lambda, the counter term for the mass, now written in terms of these 1 over epsilons instead of logs of lambda and lambda square, right? And the conclusions are the same because the counter terms will really only enter the Lagrangian in order to make a cancellation, to have a cancellation with the loops, right? But the finite part we have shown already is the same, right? The part that there's no cancellation to is exactly the same, right? And the thing is, the final messages I want to leave today is that in the end, right? Suppose we had used these two regularizations and the result on the finite parts, on the physical parts, didn't agree. What then, right? Which one is right and which one is wrong, right? Historically, what we learned in more than one case is that when regularizations disagree on physical observables, is because one of them, or both, right, are breaking symmetries of your problems, right? And with that in mind, then you promote the symmetries to axioms of your theory, right? And then you have a criteria to decide on good regularization, right? If you have your symmetry as at the quantum level, right, as an important feature for your theory, then only the regularizations that respect that will be good regularization, right? That's the main criteria, right? Also, you need to be able to eliminate it. Once you regularize, right, you have the divergences of your theory now explicit in some kind of parameter like this 1 over epsilon right here, right? Once that happens, you need to be able to eliminate that through a counter term, right? That when written in terms of Lagrangian need to be a counterterm that makes sense, which means that when you write it as a Lagrangian, it needs to be an operator, an operator in your Lagrangian that is sensible, right? It's local, it's Hermitian, it's, right? Respect symmetries, right? So that's a requirement here that we are imposing from the start, because we subtract, right? The way we're doing here, we're defining these counterterms already as subtractions of these non-physical quantities. So automatically you can translate that back into the Lagrangian and write it. But that's a hidden, let's say, requirement here, right? And many times that's the way you can actually see that you're violating symmetry through some regularization. You write it as a term in the Lagrangian, right? And then you see that that term violates some symmetry, right? That's a way, for instance, to see that Pauli-Villars breaks non-abelian gauge invariance, for instance, right? So for the rest of the videos, I mean, almost exclusively we'll be using dimensional regularization because it doesn't break the symmetries that are important for the theories we're looking at, right? It's important to say that dimensional regularization is not bulletproof, right? For instance, we did the very simplest version of dimensional regularization here, which is the one for scalars, right? Once we want to do this for fermions, right, we'll have to worry about how we generalize Dirac matrices to arbitrary dimension. And you can do that. We'll show that we can do that. But gamma 5 is a problem. Gamma 5 is a matrix that is very particular to d equal 4 and other even dimensions. So it's not easy to generalize. So theories that have some symmetry or some observable directly connected to gamma 5 can be tricky to regularize with dimensional regularization, right? Luckily for us, QED and QCD are not in that category, so both can be easily regularized to dimensional regularization, right? So that's the memo for today, and see you on the next video.